Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll introduce segments and rays and discuss some of their basic properties. This material is produced for Ohio University Math 3110-5110, College Geometry. Our topics will be the definitions of segment and ray in basic examples. We'll discuss equality of segments and equality of rays. We'll discuss relationships among segments, rays, and lines. And then I'll introduce what are called passing points and extreme points. And using the idea of passing points and extreme points, we'll take another look at the equality of segments and equality of rays. Finally, I'll introduce congruence of segments and discuss the segment addition and segment subtraction theorem. These topics are from section 3.3, Line Segments and Rays in Geometry, a Metric Approach with Models by Millman and Parker. These topics are scattered throughout that section. I don't stick to the order of the authors in that section of the book. The corresponding homework for this video is this collection of 7 exercises from section 3.3. Let's recall some important stuff from previous sections. There's a definition of betweenness for points in a metric geometry. This symbol, A-B-C, is spoken. B is between A and C. What it means is A, B, and C are points in a metric geometry, and that the following two things are both true. A, B, C are distinct and collinear, and furthermore, the distances add up in this sense. The distance from A to C is equal to the distance from A to B plus the distance from B to C. So there is an illustration of betweenness. I show the 3 points being collinear and also show these quantities that are mentioned in this additional requirement. Remember that the outside points can be reversed in the symbol for betweenness. So this symbol means the same thing as this. To say B is between A and C means the same thing as to say B is between C and A. But the middle point cannot be swapped. So given 3 distinct collinear points in a metric geometry, exactly one of the points is between the other two. So in these two expressions above, notice the point B was the point in the middle. In a previous video, we discussed this theorem about the existence of points with certain betweenness relationships. Given distinct points A and B in a metric geometry, there exists a point C that satisfies this requirement, and there exists a point D that satisfies this requirement. We discussed an illustration of that statement. Now notice that this illustration shows on its left the given stuff, just distinct points. That's all the left picture shows. The right picture shows the stuff mentioned in the claim. Let's go on. In a previous video, we discussed betweenness of 4 points in a metric geometry. This symbol, A-B-C-D, is illustrated with a picture like this, and we should add something to our illustration. We should point out what else we're supposed to notice about this, because the definition of this symbol is not in terms of a picture, it's in terms of expressions. Those 4 expressions are the meaning of that symbol. So we should highlight how those expressions are illustrated in this picture. So there's an illustration showing the symbols that are involved in the definition. Now this illustration is kind of clumsy, but the same illustration style can be useful. For instance, illustrating this fact about betweenness involving 4 points. If 4 points have those betweenness relationships, then they also have this betweenness relationship. We can illustrate this fact using a very similar diagram, but we'll use 2 of them, and that will improve the readability. So if we have these two betweenness relationships, then we have these two betweenness relationships. Let's go on. So here we are with the new material from section 3.3. First, the definition of segment. This symbol, AB with a bar over them, spoken segment AB, can be used when A and B are distinct points in a metric geometry. They have to be distinct points. And what it means is this set, the set consisting of all points C that have the property that either C equals A, or C equals B, or C is between A and B. So that could be a picture. So C equals A would correspond to C being there. C equals B, of course, would be there, but C being between A and B would be somewhere on that stretch of the set. Some additional terminology: the endpoints, or vertices, of that segment are the points A and B. And the interior of the segment is the set of all points of the segment that are not endpoints. So denoted this way, interior of AB is this set minus that set. In other words, it's the set of all points C such that C is between A and B. The length of the segment is denoted by that symbol, and it's the number AB, that is the number that's the distance from A to B. Now notice that in a metric geometry, the distance between points can be 0 if the points are the same point, but the length of a segment can never be 0, because to have a segment, you have to have distinct points. So when you measure the distance between distinct points in a metric geometry, you'll never get 0. So it's impossible to have a segment with length of 0. Definition of ray is this symbol, AB with an arrow over it, pointing in the direction of B. It's spoken ray AB. The usage is the same as the usage for the segment symbol. A and B have to be distinct points in a metric geometry. And what this symbol means, ray AB, is a set. The set consisting of all points C such that C is equal to A, or C is equal to B, or C is between A and B, or B is between A and C. That's illustrated this way. Now notice that this set consists of C's that satisfy this requirement, and in addition, some more C's that satisfy that requirement. Well, all the C's that satisfy this requirement are points C that live on the segment AB. So in other words, we can write that the ray AB is the union of segment AB and this additional chunk. So in the picture up above, that would be segment AB union this additional stuff. Some more terminology: the initial point or vertex of ray AB is the point A, whatever letter is sitting there on the left side of that symbol. The interior of the ray is the set of all points of the ray except the initial point. So the interior of ray AB is this set minus the set containing just A. So in other words, it's the set of all points C that satisfy these requirements except you cross out that one. So the remaining requirements are there. Let's do some basic examples. If we let A be the point 0, 5, and B be the point 0, 13, and C be the point 12, 5, then Euclidean segment BA is shown in this drawing. That's the same set of points as Poincare segment BA. Euclidean ray BA is shown here. We label the letters, and I put an arrowhead here to indicate that this keeps going off screen. Poincare ray BA is shown here. Observe that it's not the same set of points as Euclidean ray BA. Euclidean ray BA goes on forever in that direction. This ray doesn't. You can draw the entire ray. This open circle indicates the missing endpoint of that ray. So on this ray up here, there are some points with negative y values. On this ray, there are not points with negative y values because a Poincare ray consists of points that are qualified to be in the Poincare plane. They all have to have y greater than 0. Euclidean segment BC is shown here. Poincare segment BC is shown here. So here's point B, and here's point C. Notice that this is not the same set of points as Euclidean segment. The Poincare segment is this chunk of points. Now notice that my drawing includes the Poincare line for clarity. So this dotted thing is the Poincare line, and I really should include the description of that line. So this is the semicircular shape with center at 0, 0 and radius 13. So anytime you make a drawing of a Poincare line or line segment or ray, you really need to show the entire Poincare line with the missing endpoints and with the circle center labeled for clarity. It's not really necessary to label the line with its equation in the case of a Euclidean segment or ray. It can't hurt, but it's really helpful in the case of a Poincare segment or ray or line because they're just so confusing, the type 2 lines. To make sense of them, you really need to be able to visualize the whole semicircle of which they're a part. Euclidean ray BC is shown here. Now we would put an arrowhead on the end of this to indicate that it goes on forever in this direction. Poincare ray BC, now here there's a typo. Now again, notice that I've drawn the entire Poincare line. I should label it. Notice that I've labeled the missing endpoints and the center for that semicircular shape. And notice that I'm able to draw the entire Poincare ray. There is no arrow. There's just an open circle indicating that that endpoint is missing. The Poincare ray is this entire set of points here. Now I want to discuss equality of segments and equality of rays. Note that segments and rays are defined as sets of points that satisfy certain requirements. Therefore, equality of segments and equality of rays refers to equality of sets. That is to say that two segments are equal means that they're the same set of points. So for example, consider these segments: segment AB, segment CD, and segment EF. Now both of these segments have a length of 5 units. Segments AB and CD are not equal because they're not the same set of points. Segment AB is this set of points over here, and segment CD is this set of points over here. Those are not the same set of points. They have the same length, but they are not the same set of points. So we would write this: segment AB is not equal to segment CD. Segments AB and EF are equal because they're the same set of points. This green set of points is the set of points that makes up segment AB. It's also the set of points that makes up segment EF. So we write that symbol: segment AB equals segment EF. It's important to notice, however, that A is not equal to E and B is not equal to F. That is to say, in this symbol, the letter on the left denotes a point that's not the same as the point as the letter on the left in the other symbol. And the letter on the right in that symbol denotes a point that's not the same point as the letter on the right in the other symbol. So even though this equation is true, those segments are equal, those points are not equal. A is not equal to E, B is not equal to F. Let's go on. Now I want to discuss relationships among segments, rays, and lines. I'll just start with an example. Let's prove this fact about the symbol for segment. the order of endpoints does not matter in the symbol for a segment. So given distinct points in metric geometry, segment AB equals segment BA. Now, this is a claim about equality of sets. So its proof has to have the structure of a proof of set equality. But there's more than one style of proof of set equality. I'm going to do two different styles of proof because it's very important to realize that there are these different styles available. One might be the more familiar style, but actually another style is actually the most useful in more cases. The first proof that I'll do is this. I'll prove that segment AB is a subset of segment BA, and then prove that segment BA is a subset of segment AB. Now, how is that done? Well, remember the proof structure we have no choice about. We have to start with, suppose that a point C is in the left set. And we have to end by saying, therefore, that point C is in the right set. We have no choice about this proof structure. The proof that that green set is a subset of that red set. Now, we also have no choice about something else that has to go in this proof. This first statement we know is true. We're supposing that it's true, but it includes a defined term. That is, to say that C is an element of segment AB means all this stuff. So in other words, we unpacked that definition. Now look at the last statement of the proof. The last statement of the proof is a defined expression. Now we know that the only way that we're going to be able to get to say that that's true is to have previously proven that that's true. So that red statement is going to have to be there, justified somehow. And then once that red statement is there, we're allowed to write this blue statement, and the justification will be, well, by the definition of line segment. So we have no choice about what has to start this proof and what has to end this proof. And we have no choice about what has to come as the second statement. We have to unpack that definition. And we have no choice about what has to come here, because at the very end we're going to pack up the definition. Now you see that in the middle, where there is sometimes a gap that we have to figure out how to fill, in this proof there was no gap. It turns out that just the proof structure, the frame of the proof, and then the unpacking and packing up of the definitions, turns out to be all that we needed. The key fact is, if C is in segment AB, then either C is equal to point A, or C is equal to point B, or C is between A and B. Well, look, we can change the order in the OR statement. So this green thing can go over here, and this red thing can go over here. So there we've used the commutativity of the OR operation. But also, remember that you can change the order of the outside letters in the symbol for betweenness. That symbol means the same as that symbol. That's because of that theorem, Theorem 3.2.2. The outside points can be reversed in the symbol for betweenness. So there's our end of proof part 1. We showed that segment AB is a subset of segment BA. Now, an almost identical proof would work in the other direction. Just change the letters, and you could show that segment BA is a subset of segment AB, and that's the proof that those two sets are equal. So not very hard, but this was a very simple task to prove that segment AB is equal to segment BA is a very simple idea, and the proof was not very long. So this proof, number 1, is not very long. It might not seem like it's worth doing another proof, but I'm going to anyway, because like I said, there will be other situations where this other proof style is more useful. So our goal is to prove that segment AB equals segment BA. Well, I'll start by just simply writing segment AB. And then I'll just simply, on the right side of the equal sign, put the entire description of segment AB. That's the definition of segment AB says this is the set that is the set segment AB. Now notice, within this set we have some ORs. Remember that the OR operation is commutative, so that means that I can change the order by commutativity. And then notice also in this set description there's this symbol, A-C-B, and by that same theorem, 3.2.2, I can change the outside letters, so I can replace that blue expression with this blue expression. So I end up with this new set description, but that's just the set description of segment BA. So just 4 lines, the same number of lines as proof part 1 in proof number 1, but notice that proof number 1 was actually going to need a proof part 2. So really, proof number 1 is 8 steps, not 4. So I have fewer steps here. I have 4 steps in this proof. I would have had 8 steps in that proof. But it's not just that we get half as many steps in this second proof. For some proofs involving more complicated set relationships among segments, rays, and lines, the second style of proof is much easier. The reason is that the first style of proof would involve cases, sometimes many, many cases, while the second style of proof does not. So here's an example of what I mean. Prove this. Given points A and B in a metric geometry with A not the same point as B, the claim is segment AB is equal to the intersection of ray AB and ray BA. So we could illustrate that in the following way. So there's our picture. This segment can be obtained as the union of this ray and this ray. Maybe not that necessary to illustrate, but again, my general attitude is always try to illustrate the statements of theorems or things that you're proving, so you can have an idea of what you're talking about, and then also sometimes there's real insight that can come from being able to illustrate. Now let's do a proof in the style of that second proof. So we need to prove that these two things are equal. I'm going to start by just writing down the expression for the thing on the right. Now I'm going to replace ray AB with the set description of ray AB. Now I'm going to use the second version of the set description for ray. Remember that there was this general description of ray, that is a point C that satisfied one of those 4 requirements. But then there was this second description which was a little bit simpler. Either C satisfies this first requirement, that is, C is in that green chunk, or C satisfies this second requirement, that is, C is in this red chunk. So there's the first requirement, C is in that segment, or the second requirement, C is in that extra chunk. And then I do the same thing with ray BA. I write it in this interesting way where I have the set of the union of this segment BA with this other set of points C that are in that other chunk. Now we get to work. First thing that I do is I rewrite this symbol. Segment BA is the same as segment AB. So now both parentheses expressions have segment AB in them. Now I have to deal with this big expression that has an intersection symbol in it and 2 union symbols in it. Now you know from past experience with set unions and intersections that there's a distributive law kind of thing going on here. We're going to accomplish this big operation by doing 4 operations. So there's some intersections, 4 intersections, and 3 unions. So instead of these 2 big expressions with an intersection between them, I have 4 smaller expressions with unions between them. Now those smaller expressions can be simplified a lot. AB intersection AB is just AB. That's easy. Now, this is the cool one. Look at this expression. Segment AB union the set of all points C that have this betweenness relationship. Well, remember that segment AB consists of endpoint A, endpoint B, and all points C that are between A and B. So there are no points in this blue set that qualify to be in this green set. So this intersection is the empty set. Same thing is going to happen here. We're taking the intersection of a line segment AB, with this set, the set of all C that have that betweenness relationship. Well, same thing. There are no points C in this set that are qualified to be in this set. So that intersection is the empty set. So we have the union of segment AB with the empty set, the empty set, the empty set. So in other words, the right side is just simply a very cool proof. That's using that second style where you just play with the symbols that describe the sets that you're working with. So again, if we had tried the proof style, the other proof style, show that the left side is a subset of the right side and show the right side is a subset of the left side, if we had done that with this, it would have been really hard. Let's go on. Now I want to talk about something a little more sophisticated, passing points and extreme points. These words, B is a passing point of script A, are used when you have a metric geometry in the discussion and that script A is a subset of the set of points and B is an element of script A. In other words, B is a point in the metric geometry that is an element of that subset. So that's the usage of these words. That's when you're allowed to say those kinds of words. But what do they mean? They mean this. There exist points X and Y that are also in that set, script A, and such that B is between X and Y. That's the meaning of passing point. Now, I could illustrate that this way. So here's an illustration of a passing point. Notice that script A is this blue set, and B is an element of that set, script A, and there exist these points X and Y that are also elements of script A, and B is between X and Y. So B is a passing point of set script A in this example. Now, a more sophisticated idea is the idea of an extreme point. The same usage, we say that B is an extreme point of a set in situations like this. We have a metric geometry, we have some set script A that's a subset of the set of points, and we have some point B that's an element of that set script A. So in other words, B is a point in the metric geometry that is an element of some subset. What these words mean is that B is not a passing point. So here's a theorem. The extreme points of a line segment are the endpoints. So more precisely, given distinct points A and B in a metric geometry, the only extreme points of segment AB are the endpoints A and B. All other points are passing points. Now the proof of this is very interesting. Now note the proof structure. We start by stating the given stuff. First thing we do is that we show that elements of the segment that are not endpoints are passing points. That's very straightforward. I'll let you read that in detail. The next thing we do is we show that A is an extreme point. We're going to do that by contradiction. We say, suppose A is not an extreme point. That's an assumption for a proof by contradiction. Well, if A is not an extreme point, then what we're really saying is that A is a passing point. So we're going to assume that one of the endpoints is a passing point. that is going to have to lead us to a contradiction. Let's look ahead. We reach a contradiction, and we say that therefore A cannot be a passing point. Oh, but we have more than one case. In both cases, we reach a contradiction, and we say that therefore A can't be a passing point. And so the conclusion is A cannot be a passing point. So therefore, A must be an extreme point. So that's the structure of a contradiction proof. Let's look a little bit more carefully. Why do we end up with cases? Well, we're going to assume that A is a passing point, but that means that there exists points x and y in the segment such that A is between x and y. Well, there are two possibilities. Let's just consider point y of that pair. Either y is equal to b, or y is between a and b. Why is that? Well, we know that y is in the line segment. The line segment AB consists of endpoint A, endpoint B, and the points that are between A and B. Well, we know that y is not equal to A because this symbol requires that x, A, and y be distinct. So y is an element of the segment AB, and we know that y and A are not the same point, so that leaves these two possibilities. Either y is equal to b, or y is between A and B. Well, remember, when you have an or statement show up in a proof, you can set up a proof by cases. Either this case is true or this case is true. That's how we ended up with these two cases. Case 1 is when y is equal to b. Case 2 is when y is between A and B. I'll let you read this proof in more detail on your own. Part 3 is to show that B is an extreme point. Now, this proof is done in the book. They take actually more steps than I do. I think they make the proof harder than it should be. Usually my proofs are longer than the proofs in the book, but I think that in this case, the proof in the book is harder than my proof. Now, there is a similar theorem that's not presented in the book. The only extreme point of a ray is the initial point. So given distinct points A and B, the only extreme point of ray AB is the initial point, A. All the other points are passing points. So we now have these two theorems. The one that's stated in the book, given distinct points AB, the only extreme points of the segment are the endpoints A and B, and the only extreme point of the ray is the initial point A. Now there's kind of a freebie that if two segments are equal, then their set of endpoints are equal. Remember from before, we had segment AB equal to segment EF, even though A is not equal to E and B is not equal to F. But if we look at the set of all the endpoints, the set of endpoints for this segment is this set, and the set of endpoints for the right segment is this set. Even though point A is not equal to point E and point B is not equal to point F, we can say that the set AB is equal to the set EF. So that's actually worth presenting here. If two segments are equal, then their endpoints are equal. That was mentioned above in that theorem about extreme points. It was mentioned as a corollary. So here's that corollary presented with a proof. So notice segment AB equals segment CD, but point A is not the same point as point C, and point B is not the same point as point D, but these sets are equal. So how would this be proven? Well, let's suppose that these two sets are equal. Well, then the set of extreme points for one set has to be the same as the set of extreme points for the other set because they're the same set. So that means this set, the set of extreme points for segment AB, is equal to this set, the set of extreme points for segment CD. So there's really nothing to it. That's why I call it a corollary. There's also subtlety in the notation for the ray. Now these statements can be illustrated. It's worth doing that. So this could be an illustration of statement 1. If you have this configuration of points, array AB and a point C that's not point A, then, well, I've illustrated this statement by showing ray AC in green and ray AB in red. It's not a great illustration, but it's nice enough. Now, how do we illustrate 2? Well, I'm just going to do a single drawing. So here's a picture of a situation where ray AB, that green ray, is equal to ray CD, that red ray. And we can see that in this illustration, the initial points are the same point. So that's an illustration of statement 2. Now the proof of statement 2 is straightforward if you use the notion of extreme points. I won't do the proof here. It's analogous to this proof about the extreme points of line segments. You should be able to prove this easily. But the proof of statement 1 would be very difficult if we just consider the definitions of the sets AB and AC. Many cases would be involved, and the proof could be unbearably tedious to read. So I'll postpone the proof until the next video when we study the use of rulers and coordinates in describing segments and rays. Finally, I want to talk about segment congruence. This symbol, segment AB, is congruent to segment CD. You can use this symbol in a metric geometry and when A, B, C, and D are points. And what it means is the length of segment AB is equal to the length of segment CD. So let's go back to those segments that we considered earlier in the video. Here's segment AB, here's segment CD, and here's segment EF. Remember from before, we saw that segment AB was not equal to segment CD, but they are congruent. They both have a length of 5. So we can say that those segments are congruent. They're not equal, but they are congruent. On the other hand, segments AB and EF are equal as segments, and they're congruent as segments. They're the same set of points, and the segments have the same length. Now, segment congruence is an equivalence relation. Note that in a metric geometry, congruence of segments is a relation on the set of all line segments. So you should be able to prove that segment congruence is an equivalence relation. I'll remind you of some of the proof structure, but you should be able to supply the remaining proof structure. I'll show you the structure for the proof that segment congruence is reflexive and the proof that segment congruence is symmetric. But you should be able to supply the structure for the proof that segment congruence is transitive, and you should be able to supply the details of the proof. So remember how the proof that segment congruence is reflexive would have to go. We'd start by saying, suppose that we have a segment, and we'd have to end by saying, therefore the segment is congruent to itself. But there's some missing statements here. You'd have to come up with that. What about the proof of symmetry? Well, the proof would have to start like this. Suppose that segment AB is congruent to segment CD, and the proof would have to end with this statement. Conclude that segment CD is congruent to segment AB. There's missing stuff in the middle that you should be able to come up with. So you should be able to come up with the missing stuff here and for the structure and the details of the proof of transitivity. The last thing I want to talk about is segment addition and subtraction theorems. Segment addition says this: if B is between A and C, and P is between Q and R, and AB is congruent to PQ, and BC is congruent to QR, then AB is congruent to PR. Now I won't prove that, but I will illustrate it. So again, this theorem says if you have points ABC with that betweenness relationship and PQR with that betweenness relationship, and AB is congruent to PQ, which I've illustrated by drawing this red hash mark, and BC is congruent to QR, which I've illustrated using this green hash mark, then AB is congruent to PR, which I've illustrated using these blue brackets. So that's an illustration of that statement, Theorem 3.3.8. You should be able to come up with an illustration of Theorem 3.3.9. Now you're assigned to prove these theorems in a homework exercise. You should find that after setting up the correct proof frame and recognizing defined terms in the proof frame that need to be unpacked or packed up, the proofs won't require any clever steps to bridge the gap in the middle. The proofs are so simple that these theorems really should just be called corollaries of the definitions of betweenness and segment congruence. So again, you should be able to set up these proofs and do the details, but you should find that they're actually very short proofs. Well, that's the end of the video. Thank you.